Welcome back. Hope you're doing well. There's one more thing that I want us to be discussing here that we've already had a little bit of experience with, perhaps in a previous course. You may have seen this example of an adjoint matrix already. But for example, let's say that we have a matrix something like 1 plus I, 3, 2 minus I, and 4. Or something like this. If we have a matrix like this, we know that we can take the transpose of a matrix like this. But notice here that we have some complex numbers. This is an element inside of M2C. So here's M2 of the complex numbers here. Oftentimes, instead of looking at transposes of this matrix, often what we will do instead is we will look at what the adjoint of this matrix is instead. The adjoint of a matrix is going to be not only taking the transpose of it, but it is also going to be taking the conjugate of each term. So another way I could write that is something like this. I could take the conjugate of this matrix, and then I can take the transpose of it as well. That order, by the way, doesn't matter. You can take a conjugate first and then a transpose, or a transpose and then a conjugate. Whatever way you take it, that gives you the adjoint. So for example, taking the conjugate of 1 plus I is going to give us 1 minus I, and it does not change position because in the transpose, it's the same entry in its row as in its column. Same thing, this other entry on the diagonal, that's going to remain a 4. The conjugate of 4 is itself. Now 3, because of the transpose, is going to move down here. So we're going to write this down here as 3. Again, notice the conjugate of 3 is itself. And then finally, 2 minus I is going to be written going from the bottom left to the top right element here. So this is the adjoint matrix in terms of a 2 by 2 complex entry matrix. The adjoint matrix is useful for us because it has a lot of neat properties. Adjoints of specific operators can be, matrices can be inverses of them. For example, taking the adjoint of a matrix and multiplying it times the matrix itself makes it something that is positive definite whenever your matrix is non-singular. So there's a couple of interesting properties here. And there's even more that I won't even get the chance to go into with this video. But I encourage us to be talking about that later on, especially in case you're interested. A lot of neat things happen with adjoint matrices. But we want to generalize this in terms of adjoint operators here as well. And that's the context that we're going to be interested in today. And here's how we're going to start off that context, okay? Here's how we're going to begin all of this. We're going to start by doing a formulation of something known as the Riesz representation theorem. The Riesz representation theorem is a way of clarifying or classifying linear functionals on a space. Remember, so for this one, we're going to ask for our vector spaces to be finite dimensional. And we'll say that they have a dimension of n here. Remember that a linear functional goes from a vector space into its field. In this case, we could say that that field is the real numbers, for example. We would call this a real functional, or it could go into the complex numbers as well. That would be for a complex functional. We'll stick with real functionals for now to keep our inner products nice and neat. But here's what we're going to say. The Riesz representation theorem says this. Every linear functional, that is every function from the vector space into the field of the real numbers, L, can be written as an inner product, as an inner product in the following way. There exists an element y inside of our vector field such that vector space such that L of x, plugging in, of course, something in here from our vector space here, is equal to the inner product of x with y. Notice, first of all, that the inner product of x with y, if I'm plugging in x and keeping y the same, so y here is just some fixed element, notice that this is linear. This is a linear functional because it's linear in each in the first variable. X is linear. If I plugged in alpha x plus beta y, for example, this would be an example of a linear functional of just plugging in something for this first component and then taking its inner product with the vector y. And that's because the inner product itself is linear in the first variable. In fact, This describes every single linear functional on a vector space that has an inner product. So of course, we're looking at an inner product space here because we are needing to be able to take an inner product whenever we do this. That's what we've been focusing on this week. So with V being a finite dimensional inner product space, we get this Riesz representation theorem for this space. Now here, let's take a look at some examples here to try and get an idea of what this actually is. Let's take a look at an example. Let's take a look at L being a linear functional from R2 to R. And what it's going to do is it's going to take the vector from R2, that's going to be L of x1 comma x2. And what it has to do is has to spit out a real number. Here's the real number it's going to spit out. I'm going to have it be 2 times x1 plus x2, something like this. Notice I can't multiply x1 times x2. That would not be linear. And so I would need this to be a linear functional, and because of that, that means that I need to have these two things being added. So multiplying here, for example, would not work. That could be an easy way to think about maybe that's not a linear functional. That can be written in terms of an inner product, but it's because that's not a linear functional to begin with. So here we have L of x1, x2 is equal to 2x1 plus x2. Now, how can we write this as an inner product? Well, we could start by separating out what x1 and x2 are here and make them their own vector again. And ask, what should we take the dot product with for this vector so that we get this value back, 2x1 plus x2? Well, x1 is multiplied times 2, so why not make the x component 2? And x2 is just by itself, so why not multiply it times 1? So this ends up being the inner product of 2, 1 with x1, x2. Indeed, this is taking x1, x2 and taking its inner product with 2, 1. The vectors, of course, these being vectors and the outside brackets being for an inner product. So now here we've written an example of a linear functional, and it found out that this was actually just taking the inner product with a fixed element y. So this is holding the form of y that we had up here. This is holding that same form. Is this the thing that we are taking the inner product with respect to in order to make this linear functional what it is? We could do this again, but this time we could look at an example where instead of looking at this in terms of R2 and R, we could look in terms of C2 and C, and we could make this the functional, let's say, H of Z1 and Z2. Here, again, I could think of this as like one big vector Z, if I would like, where Z is inside of C2. But you can see I'm just breaking it apart in terms of Z1, the first complex component, and Z2, the second complex component. Sorry if that was unclear in my previous example. But when I do break that apart, I could write this as maybe a complex combination now, something like this, maybe 3 plus I, Z1 minus 4I, Z2. If I do this, then is there another way that I could write this in terms of a linear combination of these two vectors? Well, let's see what that would look like. First, I'm going to separate out the Z1 and the Z2 here and put that over here to the side, and I'm going to figure out how this sort of dot product stuff might work. Well, this kind of looks like this, doesn't it? It looks like you're taking the inner product of 3 plus I, comma, negative 4. And we're taking its dot product, if you will, or the inner product inside of the complex space with the vector Z1 and Z2. Now, here's the thing. This formula doesn't work because, again, we're in the complex numbers here. So there's something different that has to happen. Remember that this side over here is getting a conjugate. That side over there is getting a conjugate. So whenever I start writing this, I need to be writing this in terms of the complex Z1 over the complex conjugate of Z1, comma the complex conjugate of Z2. Now this formula works. In general, though, we want Z1 and Z2 to be actually our first coordinate inside of our inner product, not our second one. So that means that we're going to have to flip where this bar lies. So instead, we're going to just keep Z1 and Z2 the same in the x coordinate here. Just keep these as the x coordinate. But that means that the other two components have to get the bar instead. So I'm going to be taking the inner product of this with 3 minus I and positive 4I whenever I construct this as an inner product with C in mind. So here, for example, I've written this now with respect to the inner product on C. Remember that the way that that works is that if you have the vectors x and y, where x and y are both inside of C2. Then this inner product works by saying you take x1, y1 bar plus x2, y2 bar. So that's what's happening right here and right here. That's why you're starting to see some bars appear over that second argument of the inner products there. So what's happening here is we are looking at ways of writing these linear functionals in terms of inner products with respect to various things. What happens is that you get a vector out here, out in the front, and that vector is what gets you this inner product. Now, in general, we could do this for any type of linear functional, including my last example that I'll talk about here. Let's take this example. Let's let V be a finite dimensional inner product space. So I'll say finite dimensional inner product space. And let's take L going from V to V to be a linear operator. Okay, let's take it to be a linear operator. Then the following linear functional that takes in an element x from our vector field and pops out the inner product of Lx with y, I claim that this is a linear functional. Why is this a linear functional? Remember that linear functional means that it has to work well with addition and it has to work well with scalar multiplication. So for example, if I looked at L of alpha x plus beta y, that stuff would have to come out very nicely for this function. So here's L of alpha x plus beta y. This is equal to this. Oops, I can't use y. I'm already using it. So I'll use z or x1 and x2. That's better. So I'll use alpha x1 plus beta x2 here instead. There we go. And that allows us to focus on that. So here is what we have plugged in for this first component, and we're taking the inner product with y. Well, L is linear, so I can always break apart this first argument like this. I could write this as alpha Lx1 plus beta Lx2 and y. And then this first argument of the inner product is linear. So I could write this as alpha times Lx1 comma y plus beta times Lx2 comma y. And finally, if I look at what Lx1 comma y is, well, this is just plugging in Lx1, little Lx1 now, plus beta, little Lx2. And that exactly means that this is a linear functional. So this is another example of a linear functional. But there's a question here. Is that this linear functional given here needs to be written in terms of x, comma, something else. What is this vector? Well, this vector isn't necessarily y, because that would just mean that Lx is equal to x. That means that L is the most boring linear operator that I can think of, the one that just sends everything to itself. It could send everything to 0. I guess that does a little bit less. But here, we could ask, what is this guy right here? We know by Riesz representation, since we're in a finite dimensional inner product space, that this has to be some vector. But the question is, what vector is it? What vector is that? The vector that we're going to be calling that here is going to be the adjoint vector for this space. In fact, looking at just this L star here, we're going to be calling L star the adjoint operator. And what this is doing, oops, looks like I lost my screen capture here. Okay, we are back. So if we are looking at what happens when I pass L from coming from this first argument of the inner product over here to the second part, which I know should exist by the Riesz representation theorem, then that is known as taking the adjoint of a abstract operator. Okay, that is how that would work, is that taking the star ends up moving it and putting it over here onto the other part. Now, think about this, and this might seem a little bit strange. Everything here is valid, and we know that this all should work. We know that this is a linear operator, so that we know this should be able to be written in terms of x times y tilde or something like this, some other types of vectors here. And the way that we can describe what y tilde is by saying, okay, this is L star of the vector y that's given right here. So all of this seems like this should work pretty nicely, namely y tilde should be equal to L star y here. But the question is, how does this connect with my understanding of what the adjoint operator does? And I could give a little bit of help here because we've got our second example up here, which says that the adjoint, what it does in the complex field is two things. It does two things. It not only takes the transpose, but it also takes the complex conjugate of each term. And remember that taking the complex conjugate is important whenever you're in the second argument of the linear operator. So the adjoint operator here should make a little bit of sense because the adjoint operator, what it does is it takes bars over everything. And since we have moved L to be going from the space in which this inner product is linear to where it is conjugate linear, that should make sense for where the vector field is over the complex numbers, right? Now, in terms of this, looking at this in terms of the transpose and things like this, remember that we've also written inner products in a different way. We've sometimes written inner products xy. I'm trying to get my order right here. I believe we've written it in terms of the y transpose of x, right? Well, if we want to write that lx, this lxy in terms of this sort of formula, then we would write y transpose of lx. But how could we get that to be the same thing? Well, what if we took the inner product of x with L transpose of y? What would happen? Well, this formula here is going to be, I'm going to take x, that's our first component right here, and then I'm going to take the transpose of this. Transpose of this switches the order of everything. I'm going to have L transpose transpose. Well, the transpose of a matrix times itself is just going to be the vector itself. So indeed, these two things end up being the same. So if I move the L over to this other side of the inner product, it ends up working pretty well. Okay? It ends up working pretty well. And that's because taking the transpose putting it over to the other side is the equivalent to looking at the operator as it is on the other part of your inner product. If you were taking a transpose of everything in your second argument here, that's equivalent to taking a transpose as you move the operator over there as well. So this should give us an idea as to why this fits our notion of an adjoint matrix as well. So the adjoint operator is attempting to generalize this notion of an adjoint matrix, but we're leaving the notion that our inner product looks like this, like it does for the dot product. So this is our formula for dot product here. And instead, it's becoming more abstract. It's looking like something that's not necessarily a dot product. It's just an inner product. If we pass it to a notion of an inner product, this is known as taking the adjoint operator. Indeed, the adjoint of a transformation, L star, notice that this is an adjoint linear operator, is the operator that satisfies this equality, the one that takes L of x comma y to x comma L star of y for all x and y inside of your vector space. Now notice that for the Riesz representation theorem, for finite dimensional inner product spaces, this adjoint always exists thanks to that theorem. But the adjoint may not always exist, and we'll see an example of that near the end of this video today. Now, if it does exist, it is unique. So we can talk about the adjoint operator. We don't have to talk about all of the adjoint operators. It is unique. And in fact, it is linear, and we can go through and show that, for example. Remember that linearity of this would mean that L star is itself linear. So what would happen if I took, for example, L star of x1 plus x2, and maybe put some alphas and betas right here, and take a look at what it was when I had its inner product with y. Well, the idea is that I can always pass the L back and forth as long as I get to gain an adjoint. And as we'll see in a little bit, this is going to be equal to alpha x1 plus beta x2 of L star star of y. Okay. So this is L star star of y, and I can break this up thanks to the linearity of the first argument here of alpha x1 of Ly, and that's possible since L star star is just L, plus beta x2 Ly. And then finally, I can bring the L's back over at the cost of gaining a star. So this is going to be Lx1 with a star right here, comma y, plus beta L star x2 comma y. And what ends up happening is that this is just L star of x1, this is L star of x2, and the scalars and stuff, all of this came outside. So this works very well as a linear operator for this. Now, linear adjoint also works very well for sums of these operators. Like, for example, if I wanted to take a look at L1 plus L2 star of x comma y, then I definitely could. I could move the star over thanks to what we saw from before, and just take a look at L1 plus L2 of y. And I can break this apart as long as I'm not taking apart out scalars, because scalars would come out as conjugate if this were a complex vector field, or as non-conjugates in a real vector field. But either way, I can write it like this. All right, so something like x L1y, x comma L2y, and then I can bring the L's back over as L1 star of x comma y plus L2 star of x comma y. And then finally, I can add these back, and then grouping together the L1 and L2, I get that these two end up looking like the same operator as well. They agree on all inner products. Okay. And then finally, for L star star, the way that I can try and make this one work is I can look to see what happens with L star star in terms of x and y. Well, remember that the way that the star works, and I'll maybe write it on the other side because that might help us a little bit. Let's write it as x of L. You know what? Let's do it like this. This will help a little bit. I had to think about a little bit how I wanted to approach that. Let's take a look at L of xy, and we'll go backwards. We'll go from L to L star star. We can write this as x comma L star of y, thanks to the definition of adjoint here. And then remember that I can flip these two things together, or flip these two, flip the position of the first and the second argument at the cost of potentially needing to add a bar right above this. Okay, so at the cost of potentially needing to add a conjugate to this value. Well, at this point, I have L star, and I can move that over here. And then I can do that at the cost of gaining another star, thanks to the definition of adjoint. And then finally, I can flip their two relations, or flip these two first and second arguments here one more time to get L star star of x comma y at the cost of gaining another bar. But remember that taking two bars here is the same as just getting us back to the original value. So indeed, these two end up being the same as well. So L is equal to L star star. In general, when we're trying to prove things with the adjoint, we're going to try and involve the inner product, because that's the definition that is involved with how the adjoint is actually defined, is it's using inner products to define it. In general, when we try and prove these other properties here, we're probably going to want to do the exact same thing. We're going to want to try and get the inner product involved with each of these formulas. Whenever we have, for example, a scalar times L, we can take it out of the adjoint symbol at the cost of a conjugate over the little bar over the scalar of R. So that has to be the conjugate of R instead. We can compose L1 and L2 and then take its adjoint. And that's the same as composing the adjoints of the those two operators individually, but you have to switch their order. And then finally, the identity operator, that is the one that sends L of x equal to x. That's the identity. This is its own adjoint. And that can be checked as well for each of these using the inner product. So that gets us some ideas here. Now, the adjoint matrix is the one that we've been talking about. If you have a matrix, and this can be not just a linear operator, this can be an m by n matrix taking you from Rn to Rm. So this is the adjoint of this matrix is going to be taking all of the entries in Aij and replacing them with the entries Bij. And what each entry looks like in the adjoint matrix is going to be taking the transpose of it and then taking the complex conjugate of that number. So you can see here that Ij becomes Ji because we're flipping the rows and the columns, and then we're adding this little bar right here. Adjoint matrices share many of the same neat little things that adjoint operators do. In particular, when we're looking at an adjoint operator, the adjoint matrix that is an n by n matrix, then we can start asking about its inverse, start asking about the inverse of this matrix. And if we do this, then the adjoint of the inverse is the inverse of the adjoint. Another neat little thing, finding a connection between how these two ways of altering matrices works. In general, by the way, we get a neat little theorem for how we could write linear operators with respect to different orthonormal bases, with respect to different coordinate systems. And this is going to be an interesting type of theorem here. Let's take a look at this. Let's let L be a linear operator on an inner product space of finite dimension. If beta is an orthonormal basis for V, then if I look to see what L star is with respect to my orthonormal basis, that's going to be just the same as taking our basis of L with respect to our orthonormal basis. So writing that matrix with respect to that orthonormal basis, and then just taking the adjoint of that. So this is the one where we write linear operators on finite dimensional vector spaces as a matrix. So this is that matrix of L. So this is the matrix of that operator, written in terms of the coordinate system beta. Taking L star and writing it in terms of the coordinate system beta is the same as looking at the matrix of L and just taking the star of it. It comes nice and easily like that. The reason that that's important is this. L star is a different operator because it works differently on inner products. And it seems like if you try and operate with respect to a specific orthonormal basis, taking the star might really change a few things. Right? You might not, your columns might no longer be in with respect to the same orthonormal basis as what you had when you were working with the matrix L. But the good news is that that little hurdle there, that little kind of mental roadblock that you have to overcome doesn't really exist thanks to this theorem. And we'll talk a little bit about why this theorem is true. Okay, so let's take a look at this theorem right here. Here is our theorem. This is again talking about these matrices of these linear operators here. And the way that we're going to do this, and I could really use some extra space here, so I might try and steal some from up above. Let's see if I have any. I do have a little bit. The way that we're going to write this is we're going to start by taking a look at our matrices A and B, which describe our linear operator A, the matrix for L, if you will, with respect to this map beta, which is our coordinate map into Rn. So this A is going to be Rn to Rn, where L is an n-dimensional, is a linear operator on an n-dimensional space. Now we could do the same map here for beta, and we could get another matrix B. Right, and so we could look at L and L star. Now, what's interesting here is that L and L star are both being mapped by this beta map through here. They are getting the coordinate map so that these can become n by n matrices, where L going from V to V is just an abstract linear operator. So these are n by n matrices. Well, it turns out that A is equal to B star, that these two things are very related to each other. In fact, one is the adjoint of each other. Well, remember how these linear operators, how these matrices are formed. The way that you do that is this, right? You have beta being essentially giving you a basis, right? It's a change of basis for you going from the coordinate matrix into everything else. And the way that that works is you take L of V1, V1 being maybe your first element inside of here, and it gives you A11 V1 plus dot, 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 or maybe I should do one more term here. A of, getting my columns straight here, should be A row 1 column 2 V2 plus dot, 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 plus A1N Vn. Then we could do the same thing for L V2. This will give us another linear combination of this in terms of V1 through Vn. A to K, or N rather, of Vn. And then we could do this all the way down to LVn to get a N1 V1 plus a N2 V2 plus dot, 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 plus a NN Vn. And we've written this sort of combination of things there before because we know that when you have this system of linear equations, then you can get the matrix of L by just looking at the coefficients of each of these things. So A, for example, will be written in terms of A11, A12, A21, and so on and so forth, all the way down to A and M. So here we go. So we have this matrix here. Now, if A were to be equal to B star, we could now calculate what each of the entries would need to be for each of these things. In particular, let's go through and say that B star is written in forms of B11, B12, B21, and let's write that down all the way through here as well, all the way down to B and N. So let's keep this picture in mind. I'll try and come back to this one a little bit as we go through the rest of this, because we do have a nice little theorem right up for us here. Let's let beta be these vectors all written up like this. Let's let A be the matrix of L and B the matrix of L star with relative to this basis. Now, by definition, Aij is the ith coordinate of the vector of LVJ. Why is this? Because whenever you write these vectors, what you get is LV1 is right here, right? And LV2 is right here, so on and so forth. So you're able to write these in this form. Okay. Maybe could have switched the rows and columns on that, but I think I did okay there. Yep, I think I could have switched those too. Let me check that real quick. Okay, just returning to this real quick. I did order my indices here slightly differently. You may have caught me on this one, and for those of you who did, great job. Because remember that we had the theorem that said that each of L of V1, L of V2 should become the columns of these matrices. I had made them the rows by accident, so that was my bad. My fault on that one. So each of these should be the columns of each of these matrices. So for example, you'll see here that this is A11, A21, A21, for example, denoting the second row, first column. And that LV1 is now this first column here. This will now become consistent with the proof as we go through here. And then also LV2 begins with A12. That should be the first component of L of V2. Now these are the matrices of these transformations here. So I've changed, the only things that I've changed are now in green so that you can change those in your notes if you need to. So now let's return here to now something that is correct, which is that the matrix A is going to be equal to LV1, LV2, all the way to LVN, where these are the column vectors, each associated to where the linear transformation L sends V1 through Vn, respectively. So Aij is the ith component of this vector LVJ. The way that we could write this is that since the basis beta here is an orthonormal basis by our assumption here, is that we could write this in terms of the inner products. We have our formulas for this from our previous day, and recall that we could we can get the ith row of this matrix by just taking the inner product of Vi here on the right-hand side. Right. So in particular, if we're thinking about this in terms of Rn, for example, remember that the way that we could be doing this is if we have L, let's say, you know what, let's do this. Let's take a look at this in terms of maybe a smaller matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's take something like 0, 1, 0 as our matrix that we're going to be multiplying this by. Here's our Y transpose, if you will. Now, what is this going to do when I multiply this matrix times, or this vector times this matrix? I'm going to be multiplying through, and what's going to happen is that the ith component here is going to return what? It's going to return 0 times 1 plus 1 times 4, 0 times 7. That's going to return the ith row element right down here. So that returns the ith row. And that's because as this moves across its row, this goes down the column to the ith row. So here, for example, this would return the row 4, 5, and 6. That's because the 1 was in the second position, and hence it returned the second row. So if I'm just looking at L of Vj, for example, then I'm just looking at one of those columns. That's going to return just the jth column, and then taking the inner product of that with V sub I, that's just going to give me A sub ij. So I wanted to go through and emphasize that. Similarly, B sub ij is L star B sub j comma B sub I with all of the same setup as before. Let's connect A sub ij and B sub ij using this inner product. So if we do that, we've got B sub ij is L star B sub j comma B sub I. We can switch these two by getting a conjugate bar up here, and then we can bring the L back, just like we can with the adjoint. And then we'll have that this is LVI comma VJ. Notice that our J and I have switched places, so this is A sub JI bar now, thanks to the bar that is up here. Well, if B sub ij is equal to A sub ji bar, then that's exactly the definition of the adjoint matrix. So B is equal to A star as desired. So that this means that whenever we have a linear operator and we translate it into its coordinates, thanks to giving it its matrix, then the matrix that we get from that, if we want to look at the matrix, the adjoint itself, instead, we could just take the adjoint of the entire matrix that we get for the matrix of L. Let's keep going here with a few examples to see what this looks like in some other context. Let's keep looking at, for example, the complex field, like B equals C squared, with its inner product being the dot product. And let's take a look at the linear operator that looks something like this. This looks a lot like our beginning examples, the ones that we saw at the very beginning here. L here is a linear operator and has a matrix relative to its standard basis given by this. Well, because this is the matrix relative to this with respect to the standard basis elements, we have 1 and minus 2i, for example, as to where this sends this first component here. Then we can see that this is going to give 3 and I as well in the second part. Then if we want to find, since the standard basis is orthonormal, meaning just the standard basis for the complex numbers, 1, 0, and 0, 1, now multiplied by complex numbers, potentially on the outside here. The matrix of the adjoint is just going to be the adjoint of A. So we can just flip the rows and the columns and then take complex conjugates of each entry that is given here inside. So whenever I want to write what L star is, I could write it in terms of this. And that gives me what L star is equal to as a linear operator on C2. I can get the formula for L star by first translating it into the matrix of L, and then taking the adjoint of that matrix and then rewriting what that matrix is in terms of its linear operator, essentially just writing out what each component yields when I multiply this matrix times Z1, Z2. All right. But we could also do this in functional spaces. Here, for example, with C infinity, we could ask questions about the adjoint for another linear operator. What about the linear operator of taking a function to its derivative? Seems like an interesting one. In particular, it seems like this one doesn't have the same sorts of qualities as the ones that we've seen before. Before we were taking Z1, Z2, we were just multiplying certain numbers here and there and things like this. And we also seen the derivative have some other strange properties in terms of its null space and its range space as well. We've talked about this linear operator a few times. In particular, we talked about this as well as the second derivative operator. Let's see if we can find an adjoint operator for this value right here. Well, first, we'll try and figure out what L of f comma g looks like. That's going to be the integral of a to b of f prime of g. And we can use a quick integration by parts formula to move that over to talk about g prime as having the integral here. And if we do that, we can write that one more time using the fact that f of x, g of x is now being evaluated going from a to b as a constant plus this new inner product. Namely, here you see that this is minus g prime, so the minus is moving over here, and that L of g is exactly g prime thanks to how L is defined. And we're taking the inner product of f and L of g. Now, if g of a or g of b is not equal to 0, for example, if we're looking at any kind of function where this ends up being a, for example, where this ends up being a non-zero constant for some values of f, well, then there's no way for us to be able to write this value as its own inner product, right? So this constant in particular has to be taken care of somehow in order for us to be able to write that LF of G is equal to F of, say, whatever something this is, times G, right? In order to find out whatever this L star should be inside of here. If this were 0, if this were not here, we would be done because we could say, okay, well, minus L is L star, and that could be a very legitimate example of an adjoint of this operator. But the idea is that the unfortunate thing is that we have to take care of this constant here to make this work. Namely, we'd have to write this as its own inner product so that we could add these two things together to become one, and then we could write this as an adjoint here. Unfortunately, there's no such function that allows us to do this. And the reason for this is that I see no reason for this to be particularly, and I'll check this real quick while I'm doing this. I see no reason for this to be particularly linear, right? If g of a or g of b in particular is not equal to 0, this may not necessarily be linear, right? And because of this, because g here is just going to be something arbitrary, that means that we cannot get an operator that works for any G that I have in my second argument. And so because of this, the operator here is not going to have an adjoint. This is an example of a particular linear operator that will not have an adjoint on this space. So that kind of gets us a little bit around where the adjoint operator is trying to get us. We've seen a good number of very concrete examples. We've seen Rn, we've seen generic abstract ways of looking at these operators whenever they can be written in finite dimensional vector spaces in terms of their coordinate matrix, then it's easy to work with them. And then finally here in an infinite dimensional case, we've seen an example where the operator does not need to have an adjoint, something where we cannot write this as an inner product where the operator is on the opposite side of the argument for the inner product. But that will do it for me today. Thank you so much. Have a wonderful day.